I am Harrison. I work at Wellcome, specifically the Wellcome Collection. The difference between the Wellcome Collection and the Wellcome Trust is one that you might already know. Hands up, anyone who's been to Wellcome Collection? Yeah, a good few. Everyone else, come along. It's a few stops away on the Circle Line. We're up by Euston. This is the outside of the building. This is the inside of the building. It's all very open and friendly and nice. We have lots of interactive activities. The famous reading room there. And we also have a lot of more traditional gallery spaces and experts who can tell you all sorts of interesting things about the history of health and how that has been expressed through art and kind of typical museum collections through history. Yeah, we have this kind of stuff upstairs, and then downstairs, hidden away underneath Euston, are the stacks. The rare books that are not out there for people to grab off the shelves that are requestable. And we also have photographers who like to push trolleys around and pretend that they're cataloguers. All of this stuff is being digitized progressively, quite fast actually. We are working with the Internet Archive, who are producing around 10,000 images a day of this material. It's a lot of images. It's basically too many images for our catalogers to get through. 10,000 images a day, or kind of 350,000 a month, is way too many for the catalogers that we have to produce detailed catalog descriptions for all of those works. But when they are digitized, when they are cataloged, they end up on the website. If you click up at the top there on the collections page, you can go here and you can search for books and pictures. If you search for something like cat, you might get a result like this. This is a cat preparing for surgery. These are some much happier cats. Searching for horse gives you results like this. The projection is not fantastic, but I think you can still make out. Wellcome is a very weird museum collection. It's stranger than most. Some of you might have already spotted the weird thing here. This horse has 2 human feet. I have no idea why. It doesn't explain why in the catalogue description. Why this kind of centaur, I don't know. It's definitely the worst of all types of half man, half horse. Like how it runs, I don't know. Yeah, but nowhere in this catalogue description does it say that this horse has 2 human feet, and that's a point that we'll come back to again and again through this talk. We also have lots of pictures of skeletons, so many skeletons. I've learned so much over the last year about different depictions of death through the ages. Unexpected domain for a data scientist to be in. We also have loads of text. A lot of the things that we're digitizing are books. And when you photograph a book or a page of a book, there's a lot of text on there that you can OCR turn into text. We have books about gelatin cookery. If you've ever wondered about how people used to cook with gelatin, we're the place to come, apparently. Witch stories as well, got plenty of those. So we have all of our images, we have all of our text, and here in the middle we have images with lots of lovely metadata. Over on the pure text side, we have all of our catalogue descriptions and pure text records like archives that don't have any visual material associated with them. This starts to present a problem. Some of you might have already intuited what that problem is. It's that stuff over on the left, the images that have no text associated with them. Because image search, when you type a bunch of words into that search box, doesn't search for images. It's a lie. We've all been convinced of this lie by Google and how fantastically closed that system is, how it just works. But image search does not search for images. Image search searches for text about images. When you type in that search box, the search algorithm doesn't go and look at the images themselves. It goes and checks whether the words that appear in your query match the words in the captions or the descriptions of those images. So all of that stuff over on the left-hand side, we can't get access to. To the algorithm, they are invisible. If they have no text associated with them, we can't see them. We can't connect researchers to those corners of the collection. Coming back to this guy, when I put together this presentation and I want to find this image, I can't find it by typing out a horse with 2 human feet. I have to type a horse with a long mane standing in front of a battle, which is weird because it's not what I'm looking for. It's not the interesting thing to me about that image. So when I arrived at Wellcome, I thought there's a pretty obvious solution to this problem. We surgically modify our catalogers so that they can type at 1 million words per minute, and we just catalog everything to the complete exhaustive extent that we need. But you know, it's Wellcome. They fund a lot of medical research, and apparently medical ethics is a thing, so that's off the table. So we turned to computer vision instead. We're going to kind of deviate a little bit into image feature embeddings, word embeddings, that kind of thing, descriptions of how they all work. Now and then hopefully emerge in a bit to explain how this is these are the components of a solution to this problem. So, image feature embeddings. This is a kind of hand-wavy working description of what image feature embeddings are, but they're kind of like the DNA of an image. You have, for a particular image, an array of numbers that express certain features about what are the content of an image. So for an image of a dog, like this, you would produce an array of numbers using a neural network, a standard off-the-shelf thing like VGG or a ResNet. And for an image like a dog, you would expect to see high activations in the features that express things like fur or grass or ears or eyes or paws. And you would expect to see similar activations for an image like this of a cat. It also has fur, it also has eyes, it also has grass and paws. For a different image, like an image of a car, you would expect to see different levels of activations in different indexes of that array. You can think of these feature vectors as positions or coordinates in a high-dimensional space. So our dog image would be positioned here in the complete space of all possible feature embeddings. Our cat might be nearby because it has similar features, but our car would be somewhere completely different because it has different features. Word embeddings do very, very similar things, but for words. So they try to capture the way that words are used or tokens are used in natural language, the kind of context that they appear in, and the semantic meaning of those words based on what's around them. So similarly, for dog, we would expect it to be quite close to cat, and car to be somewhere else because they're used in different contexts. They have different meanings. So we have our ingredients for a solution to this problem. We have our image feature vector space and our word feature vector space. But they are very, very different spaces. They are produced using totally different methods. They have totally different dimensionalities. And in theory, it's very, very hard to connect the two. There's this thing that is referred to very often called the semantic gap that refers to the fact that these are different spaces and they encode different things. Bridging the semantic gap is supposedly a very hard thing to do, but it's kind of not, unintuitively, or in refutation of the literature. We have a lot of examples out there of data sets that connect language and images. And if you think about what these feature vectors are, they're just arrays. They're just embedding layers. And that's all that neural networks really do, is they connect different dimensionality feature spaces together. So using these examples of an image and a word, we can extract the feature vector for the image and position it somewhere in feature space. Look up, using a standard library of word vectors like glove or fast text or word2vec, look up the word vector for dog, and we can connect the two. We can do the same thing with cat, and we can do the same thing with car, and we can do this again and again and again for thousands of different examples of thousands of different class of image and word, and eventually learn a mapping that connects image feature vector space to word vector space. And once we've done that, we can take a new image, extract a feature vector for it, even if it's within a class that we have never seen before, and we can predict where in feature vector space it's going to be, where in word vector space, sorry, it's going to plausibly turn up. And we can make some kind of inference about what the kind of word that describes that image is going to be. That's how image captioning works. That's how classifiers work, image classifiers. You just add a softmax layer to that, and that's your classifier. But we can also go the other way around. We can take a new word that we've never seen visual examples of before and map back into image feature vector space. And that's basically image search. You take a word that you've never seen before, and you try to match it to some visual material, return the nearest neighbors to that position that you're guessing the right kind of material is going to be in, and it works. Magic. This is a technique that was proposed in a paper in 2012 that came out of Google called Devise for Deep Visual Semantic Embeddings. And it's kind of flown under the radar for a long time, but it's a really powerful technique and it does work. At this point, though, there is quite an obvious question. What happens if the user gives you a query with more than one word? How do you encode a more complicated situation than things that fit within the standard word vector libraries that we know and love? And the solution is one that has popped up in the last year or two, sentence embeddings. They've been getting a lot of attention. Models like BERT and InfoSent and GPT-2 have been getting all sorts of attention because they solve this problem. They do roughly the same thing as image feature vectors and word vectors. For a sentence like "the cat sat on the mat," we would expect to see similar activations or similar levels of activation in similar features to "a kitten on a rug." Even though none of the words are shared between the two, they have similar meanings. We would expect to see them in similar positions in feature space. And a different sentence like "this film is bad" should appear in a different region of feature space. And that's what we see with models like BERT and InfoSent. We have the cat on the mat and the kitten on the rug quite close together, and the film being bad in a different region of space. Like I said, there are these big models out there called BERT that are very popular. I'm going to say some bad things about BERT, which is why this GIF is here. We are using not BERT, partly because when we were doing this work, BERT hadn't been released, and the current state of the art at that time was InfoSent, which is a model that was put out by Facebook. InfoSent also allows us to get over some of the problems that we have with BERT. The principal one being that sentence embedding models are pretty bad at encoding very short sequences. While they perform fantastically with a set of tokens that is 5 or 6 tokens long, and they can encode all of that semantic complexity, if you give them a sequence that is 1 or 2 words long, they really struggle to add any kind of valuable meaning to that. They can't perform the same function as word vectors. So we want to produce some kind of sentence embedding model that retains the complexity of the long sentences, but also encodes the same amount of complexity for short sequences. The way that InfoSent is trained allowed us to do that. We made a small modification to the input data, retrained InfoSent, or continued training InfoSent based on the model that had been open sourced, and it worked. And we can now show you some results. So again, the model, or the results that you're going to see here, are based on absolutely no text whatsoever. Computer simulations of proteins and other molecules. Again, the screen is really bad here, so you can't really see this. But these are. And the model has no access to any text about these images. It is purely looking at them and returning results based on its understanding of language and its understanding of how that language maps onto visual features. Text written in Hindi. I don't know whether any of this is Hindi, but it's a pretty good guess. Yeah. Photograph of stone arches in a church. It's not bad. MRI scans of brains. Some of these definitely aren't, but some of them definitely are. Really horrible, disgusting drawings of skin diseases. As I said at the beginning, the Wellcome Collection is a medical museum, so we have a lot of really grim stuff. Avert your eyes if you don't want to see this, because it does work. Ready? Moving on. Pretty drawings of plants and flowers as some eye bleach. Again, it works. We have tons of botanical stuff as well as the horrible things. Astronomical charts of the moon, pretty good. Surgical instruments, bang on. Intricate drawings of skulls, not bad. Collection of blood cells, I can understand where it's coming from. A cat preparing for surgery. We've got our old friend right up at the top there. An old wooden boat, pretty decent. And my favourite of all of these results, skeletons in excessively dramatic poses. I don't know why this is a thing. It's bizarre. We have so many of them. I don't understand why, if you're learning about anatomy, you have to have so much drama involved. But it's a thing. Yeah, we have tons of these. Come and see them. They're a lot of fun. So there is a caveat to all of this. When we were developing this, I did a lot of this development. I got the model to that stage that you just saw and was very happy with it. I had a standard set of queries that I would put into this model. I could see whether it is returning good results. I was assessing it against standard academic data sets and calculating metrics based on all of that, doing all the good things. But we then rolled it out to a wider set of internal stakeholders. Basically, we showed it to the catalogers who were eventually going to be using this tool. And while I had done some early testing of feeding it absurd scenarios like this, cows on the beach. You don't expect to see pictures of cows on the beach. I know that we don't have any pictures of cows on the beach in the collection, but I wanted to see what it was going to return. It doesn't return cows on the beach, but it does return hippos in rivers, which is, like, fair. It's not the right result, but you can see what it's getting at. But we're edging closer and closer and closer to a kind of Google Gorillas situation here, which is not somewhere we want to end up. And like I said, we rolled this out to our catalogers. We produced a little demo for them that they could interact with. And one of the queries that they input to this model was birthday cake, which seems very, very innocuous. Like, you wouldn't expect anything other than birthday cake to come back as the results to this query. But a thing that I hadn't accounted for at the time was how tightly clustered all of the food words in word vector space are. I'm going to listen for people to giggle or gasp as you get where this is going. So we have very, very tightly clustered food words in word vector space. So the word for cake, or the feature vector for cake, and the feature vector for meat are very, very similar. The machine has trouble distinguishing between the two, because in natural language, they're used in very similar contexts. But the machine then carries over that kind of close association or misunderstanding into the visual world, and also has trouble distinguishing between perfectly beautiful steaks and horrendous pictures of surgery. So the results that people were getting back for searching for birthday cake were things that look like that, but unpixelated. Not a thing that you want to do to your users in the real world. So that's a brief caveat. I am going to leave off all of the kind of heavy stuff and recommendations, because we've already had a fantastic day of very serious talks about how to address these kind of things. I'm going to leave it light here and just say thank you for listening. We're also hiring. If any of this sounds fun to you, if you want to build the infrastructure that powers this, and hopefully a good version of this, and also lots of other fun models, and you know a bit of Scala, come and talk to us. Thanks. Do we have any questions? One at the back?
So relating images and text obviously goes two ways. In one direction, you're trying to get a caption, and the other, you're trying to sort of search for an image.
Yep.
I can see how, in the captioning case, it would make more sense to use a sort of sentence embedding-based model because you're trying to generate something more like natural language.
Yep.
But going the other way, often people's search queries are actually they're just sort of fragments. They might just be a few keywords.
Yeah.
Had you considered, or did you try, rather than using sentence embeddings in that way, just using a sort of centroid, for example, or some sort of weighted average of the word embeddings or people's search queries?
Yes, we did try that, and it's a much simpler solution. It doesn't work quite as well as this model that we have produced to capture the complexity of longer queries, especially on those longer queries where people are really adding context. But yeah, the majority of queries that we get are single word, and then the majority after that are two words that are usually nouns. So yeah, in the majority of cases, that is a much simpler solution to this kind of thing.
Cool, thank you.
No worries.
Anybody else?
Down the front here.
It's two questions, basically.
Yep.
One is very simple. Can you find the horse?
No, you can get a lot of other horses.
But horse with feet is not going to get it.
No, sadly not. They're not big enough feet.
Which leads me to my second question. Clearly, the image classifier is based on a very broad data set, whereas the Wellcome Collection, which I'm familiar with, as you say, is full of a lot of brilliant, gruesome images and dancing skeletons.
Yep.
Is it possible to tag and partially retrain the image classifier? It's a bit more skewed into a Wellcome direction.
Yes, so we did that. The initial word-based thing is trained purely on ImageNet. Then the thing with sentence embeddings, we start to add in Microsoft Cocoa, the image captioning dataset. And then once that model is working well, it's robust, it's performing well on all the metrics, we do a bit of transfer learning to add it into, to slide it over to the Wellcome domain. It does quite well with the variants, I hope you agree. But yeah, the variety of stuff that we have in the collection is so broad. Luckily, we do have a lot of stuff that is captioned well, that does have works that are well titled. So there is enough material to do a bit of that transfer learning. All of the examples are produced from a held out set, so no overfitting going on there, I hope. But yeah, we do a bit of that transfer learning.
So I'm not sure how old the Wellcome dataset is, but do you have any problems dealing with the change in language over time, as in if the meanings of words can change, so does that affect anything?
Not in this particular example, but it is a thing that we deal with quite regularly in other problems and other data sets. Yeah, it's huge. Spelling. Before spelling unified, it was just chaos. No one knew how to spell anything, and trying to apply word vectors to that kind of thing is just very close to impossible. Yeah, it's an interesting problem though, and not much work is being done on it.
Sorry, one more question, please. I think I saw one in the middle. No?
Oh, that was really interesting, thank you. I was wondering basically what you were planning to do next? I mean, you mentioned about how you were going to be using the tool with the cataloger, so I'm just intrigued about.
Yeah. So because of the kind of unexpected nature of some of the results that you get back, I don't think it's ready to be swapped out for the standard Elasticsearch thing that we have going on the front end. We're not going to be rolling out to the public, but it is a really useful, or we think it's very promising as a tool for catalogers internally to get started on cataloging that material. If you can constrain that data set so that you're not just dealing with the chaos of the entire collection and just catalog the horses. Say you are a horse domain expert and you know all of the things that should be annotated on a record about horses, you can deal with all of them in one go. That kind of approach has been really useful in other domains, particularly text. So doing that with visual material seems promising as well.
All right, that's all for question time. Thank you, Harrison. One more round of applause for Harrison, please.
Thank you very much.